So in the last class, basically we have discussed about the methods on Rallies method and the Holzer method, right? Okay. And Rallies method, as we have already observed that we can find out the fundamental frequency, although it is underestimated, okay, because it's approximate. That is an approximate way of calculating the fundamental frequency, Rallies method. Then Holzer method, we have seen it is an iterative kind of method. Okay. You have to assume some natural frequencies, right? That omega 1 per eigenvalue you have to consider, and iteratively you have to see whether xn plus 1, right? Whether that is getting 0 or not. Okay? And I have also shared with you an Excel sheet where I have done for a typical example. Okay? So that type of similar Excel sheet you can create as per your convenience and try to solve similar type of problem. I have taken an example, numerical example of a 3 degrees of freedom system and solved that. And also we have or we have verified that the Dunkel's method giving the system in the fundamental frequency, which is lower than the actual. That stupid fellow. Okay. Someone is unmuted. Anyway, so now today we are going to talk about so there are few methods still remaining, like the matrix iteration method, Jacobi's method, and finally the most important is the Rallies method. Rallies method, you need to understand the concept also. But before that, as I already mentioned, that in this chapter that we are understanding, that is the finding out system natural frequency and mode shapes. Okay. So here the theory part, you don't have to be much concerned about that. Okay? You have to know how to apply that basically, right? Application need to be more thoroughly understood, and you should know how to solve problem for this. Okay, that is the more important at this level for you. Okay, but you should know how it is coming at least. Okay, that is the thing. Okay, so then now we move to the third method, that is the matrix iteration method. Okay, so in this case, at a time we will get one frequency and as well as mode shape. Okay, so let's see how it is. So our eigenvalue problem, as it is already mentioned, you see, so k into u equals to omega square mu. Okay, so let me just tell you one more thing, is that so whatever we have learned the concept in structural dynamics regarding single degree of freedom system and multiple degree of freedom system, those are quite important. Okay, and these are we are going to use again, similar type of thing we are going to use, or we are going to derive for continuous system, which will be our next topic actually. Okay, and last topic basically, the continuous system. And for continuous system, in this elementary level of course, you have only the beam analysis, and that is also Eigenvalue analysis. Okay, so I am again repeating, if you have any difficulties in understanding on those things, the single degree of freedom system or multi degree of freedom system, especially the eigenvalue analysis, how to find out the natural frequency mode shape, how to formulate the equation of motion, and then orthogonality of the mode shapes, then mode superposition theorem, and how to find out the response finally. Okay, so those need to be thoroughly understood. Okay, because you will see, and as you can see in this at present also, we are repeating the same thing, right? Same formula we are using, right, in some different manner. Okay, to find out the natural frequency mode shapes. We have not discussed about any new theory like that. Okay, and you will find that in continuous system also, that we are going to discuss in the next, you will find out similar type of example. Like for example, just I will show you, although we will discuss those things in detail later. I'll just show you. So what is the orthogonality relationship? We have here discussed that UR transpose M into US. If R is not equal to S, then it equals to 0, right? We have seen this. This is the orthogonality relationship for a discrete multi-degree of freedom system. Discrete system and multi-degree of freedom system. Where M is the mass matrix and UR and US is the two different mode shape are not equal to it. Mode shape or eigenvector. Okay, that's the orthogonality, mass orthogonality. So similar type of expression for continuous system, that will not be in a vector form, right? Because here, since the system is discrete, one discrete spring, discrete mass, like that, right? So there it is a continuous, like a cantilever wave, right? It is a continuous property or distributed property. It is a discrete parameter system. It is a distributed parameter system. So in this case also, the orthogonality relationship valid, but the orthogonality relationship will be in that case will be integral. If L is the length of the beam, then 0 to L mass per unit length mx. If it is varying along the length, then there it is the eigenfunction. It's called eigenfunction urx usx dx equals to 0. You see similar type, right? So that relationship exists. Okay. You see, in reality, please be in the mute mode. Okay. If you want to ask any question, then you unmute yourself. Okay. Okay. So you will find out that similar type of expressions will derive there. Okay. So that is what it is very important to understand the multi-degree of freedom system and all the associated derivation or concept. Okay. So now let us go back to our present thing. That is the matrix iteration method. How to find out the natural frequency and the modes. Okay. So please look at carefully. Okay. So this is our eigenvalue problem, right? Now I can write k inverse m into u equal to 1 by omega square u. This line is also okay. I am defining k inverse m as d, okay, which I am calling as dynamical matrix. So the d into u equals to lambda into u. So this is generalized eigenvalue problem. This is the actually standard eigenvalue problem. Okay, and it can be shown from linear algebra that if you solve this eigenvalue problem, that is equation number 12, this will always, okay, this will always lead to the highest eigenvalue. Okay, so that means you will get a highest value of lambda. Okay, highest lambda. Always, if you do the you do the eigenvalue analysis of this thing, that is the matrix iteration method using, you will get the highest eigenvalue. Okay, highest value of lambda. Let me write it lambda, highest of lambda. So if you get the highest of lambda, then the problem that we are considering, our actual problem is this, right? Okay, so what frequency you will get always if you consider this problem? What frequency you will get? If lambda you got highest value of lambda,
highest frequency.
Highest frequency, how it is? Can you explain me, please?
No, sir, it will be lowest since lambda is 1 by omega square.
1 by omega square, right? So I will get the lowest eigenvalue, that means the lowest frequency. Is it clear to everybody? Okay, so that means I'll get the, what is the lowest frequency? It is the fundamental frequency. Correct? It is the fundamental frequency. Okay. So we'll start with this equation. Okay. So let us see what is the procedure it is. Okay. So just look at the procedure. You should remember the procedure. Okay. That is good enough for you. Okay. So d into u equals to, what is that? Lambda into, that's one. So as a trial vector, we'll choose u. Okay. Let us consider the 3 degrees of freedom system. So we'll consider a trial, first trial ui. So now I will write it ui here because it's a trial, right? So trial, I'll choose anything 1, 2, 3, 1, 1, 1, whatever. For 3 degrees of freedom system, for n degrees of freedom system, n such entries, any trial. Then you obtain the values of d into that ui, first ith iteration. We'll get some vector, right? So I am giving as an example of 3 by 3. Okay, so we'll get a vector. We multiply d. What is d? D is k inverse a as a dynamical matrix, right? Okay. So we'll choose a trial, anything, doesn't matter, and then you obtain this vector. Then you make the first component, first entry, unity. That is either plus 1, minus 1. So if it is come out to be, let's say 5, then you take out 5. Okay. So I mean, you write 5. So this entry actually divided by 5 and all other entry in a similar. Okay, just take out 5 common. If it is 5, if it is minus 5, you take out 5. Okay, then it make it minus 1. Okay, understood? Only the first entry you have to normalize like that. Okay, so then actually this will represent your lambda, but you have to repeat the thing. So then you will get this vector, right? So now in the next case, so that I am calling as u I plus 1. Okay, the next time you will get d into u I plus 1. Again you will do the same, some vector you will get. Take out the first one common so that it becomes plus or minus 1 depending on the sign. Okay, and repeat the procedure unless the difference between this and its previous one is negligible. Okay, let's say you got 5 and here you got 5.001 or something, then you can stop the iteration there. Okay, if it is not there, there is a substantial difference, proceed ahead again. So you'll get some vector, so that will be your u again I plus 2, then you multiply d into u I plus 2, get some vector, take out the first one common so that it becomes plus or minus depending on the sign, and check with the previous step whether this is close or not. Okay. So any difficulty in understanding what is the procedure? Very simple, right? So let us do the same example that you have done. Okay, and then it will be you will find that is very simple. Okay. So what is the K and M matrix for that problem that we discussed in the last time for the Holzer method? So I think I have given a problem like this, if I remember correctly. Okay. It was K1, it was K2, it was K3, it was M1, it was M2, it was M3, and I think K1, K2, K3 are 1, right? And M1 is 1, M2 is 2, M3 is 2. Am I correct? This, just check it. Okay. This one. The last time that we discussed the problem using Holzer or the Dunker release. So if these parameters are used, so construct the first the D matrix, right? So first construct mass matrix that we have already constructed in the last class, K matrix. Then found out the dynamical matrix, that is K inverse M, and do the procedure that I just discussed. Okay, and then you will find out the first eigenvalues and eigenvalue and eigenvector. Okay, so once you got this lambda, then lambda is equal to 1 by omega square. You can find out omega, right? Lambda is 1 by omega square, right? Correct. Anybody has any difficulty in understanding this matrix iteration method? It is not over yet. So you get the fundamental frequency of the first frequency. Now how to find out the second and third frequency or more frequency for n degree of freedom system? Okay, because as I told, from the linear algebra you can show, you will be able to show that this will always lead to the highest value of lambda, that is lowest value of omega. How to find out the other modes? So that is called the matrix deflation. Okay, so that we'll discuss. But let us first find out the fundamental frequency for this problem. Okay. You have already, you have calculated that the first frequency I think is point around 36 or 366 something is there. And if I remember correctly, using Dunker release method, we got omega 1 as the 0.33 or something, right? 333 or 33 something, around that. Okay. An exact value is I think 0.36 radian per second or something like that, 366 or 366. So that you can check quickly. Okay. So if you have any difficulty, please ask me. Okay. The procedure you understood, right? It is very simple, as simple as it. Anybody has any doubt? Any doubt? And by the way, I have not checked the assignment yet, but just while downloading few of them, I just quickly roll my eyes over the first page, and it is really shocking to see that. And people said, first of all, copying that I do not have to go into the deep. Just by seeing the first page, I can conclude that many people had copied. Okay, that is one thing, and another thing is that I have asked you to write the equation of motion using Lagrange approach, right? I don't know whether you are reading the question paper or reading the other answer script, but just randomly copying and doing the using free body diagram. Okay, Newton's law. Okay. So it's absolutely unexpected. Anyway, but that is not expected from, from you, and you are from a reputed institution, right? NIT teaching. So it is really shocking for me to see that. Okay, so if anybody has difficulty here, you can ask me, or otherwise you please do the procedure. Maybe in 4 or 5 iteration you will find out that you will see that there is a convergence. Okay? That is the beauty of this method, matrix iteration method. So please do the problem. So this is the same problem actually, right? Last time we discussed, okay, using the Dunker method and the Holzer method. Any difficulty in understanding the procedure or what I'm asking you to do? Anybody? Or should I repeat what I tell so far about the procedure and the matrix iteration method? You have to speak up. Okay. Otherwise, I assume that you have understood everything.
Sir,
Yes.
can you repeat it once? Like there was a test going on, so I could not.
So why you are not now you are saying, right?
No, sir. Like I joined 5 minutes ago. There was a midsem going on.
Yeah. So you should tell me that. Sir, please repeat. Okay.
Yes, sir.
Yeah. So this you understood it, that I am just forming the general eigenvalue problem to the standard eigenvalue problem, that is d into u equals to lambda into u. D is my k inverse m is the dynamical matrix. This is clear. Okay.
Yes, sir.
I want to iteratively find out using the matrix iteration the fundamental frequency. Okay, because from linear algebra it can be shown that it will always lead to the highest value of lambda. Now highest value of lambda means lowest value of omega square, because 1 by omega square is lambda, right? So that means I'll get the lowest value of omega. Lowest omega means omega 1, that is the fundamental frequency. Now how to do that? So this is my standard value problem. Okay, d into u equals to lambda into u. So I will assume any. So I am just, as an example, I have given 3 by 3 system. Okay, anything ui first as a trial eigenvector I'll use 1 2 3 1 1 1 3 2 1 whatever, and then I'll obtain what is d into u. D is known to me by d equals to k inverse sum. Okay, so I'll multiply it. I'll get a vector, right? Because this is 3 by 3 for 3 by 3 system I'm talking about. Okay, 3 by 1, so I'll get a 3 by 1 vector. So I'll take the common. Okay, common from the first one, such that the first entry becomes plus or minus 1 depending on the sign. So if it is, let's say 5 if it came, then I will take out 5 outside. Okay, if it is minus 5, then I will take minus 5 outside and it will be minus 1. That is what I am trying to say. So you need to make the first entry plus or minus 1. Okay, accordingly, so other entry is also scaled down, right? Or scale or whatever. Okay, so I will get ui plus 1. Then I will obtain d into ui plus 1. That means this multiplied by my D matrix. D matrix is constant, right? I already obtained. That is one time calculation. Then D multiplied by ui plus 1. Repeat the same procedure. Again take out common so that it becomes plus or minus 1 depending on the sign. Okay. And now check it whether this is very close to this. Okay, or not. Okay. If it is close, then stop there. That will be your lambda. Okay. If it is not close to that, again repeat the procedure. That means this multiplied by D. D into u I plus 2. I am calling this as u I plus 2. Okay. Then again take it common and check with the previous one whether whatever the factor you have taken outside, whether these are converging or not. Once it's converged, you stop it there. So that will be your lambda, and from that you can find out your fundamental frequency. Clear?
So like what tolerance value will take that its comparison is okay?
That depends on the situation, but you will find out. You will see, let's say you have got here it is 5 and you get 5.01 or something, or 0.001. So that you can stop. Okay, you can go for further accuracy obviously by doing continuous iteration. But at present, during the class session, it is not possible, or by hand it is very difficult. Okay, that you have to write a program or something. Then whatever accuracy you want, the different you can set the difference like between these and these as, let's say 0.1% or 0.001% as the difference. So as many as accuracy, strict accuracy you want to keep. But for hand calculation, you just practice it so that you got the idea or you got the feel of the problem. Okay.
Okay, sir.
So please solve the problem that we have done in the last class. Okay. And for that, if I remember correctly, we got the exact fundamental frequencies 0.36 or 366, and using Dunn-Kirilis method, we obtain 0.333 radian per second. And I hope this is the problem, I think. Okay. Just check with your last class notes or whatever whether this is the problem or not. So anybody obtain it? Or please speak out if you facing still any difficulties in understanding. Yeah, so please tell me somebody. So what trial you are considering? UI. First tell me what D you got. What is the dynamical matrix? Yes. What is the dynamical matrix you got?
So 3, 4, 2.
3 row wise, right?
Yes, sir, row wise.
3, 4,
3,
2.
4, 2, 2, 4, 2, 1, 2, 2.
2, 4, 2, 1. 1.
1, 2, 2.
1, 2. So this is K inversion. Km is very simple to calculate. Okay, that we have already calculated in the last time. So what iteration, first iteration UI you are considering?
I'm taking it 1, 2, 3, 7.
1, 2, 3. You can take anything. 1, 2, 3. I've just as an example. This is as example. Okay. You can take 1, 1, 1. 1, 2, 5. Whatever like you like. Okay. Okay. 1, 2, 3. So you just multiply it. So what you got D into UI?
So yes? 17, 16, 11.
17, 16, 11. So you take out 17 comma 1. Then what will be this and this? Tell me.
Point 9411.
0.9411. Next one.
0.647.
Now this multiplied by D. D multiplied by. Now this will be your U I plus 1. So D into U. So I am writing here 1 instead of 1. This will be your 2 actually. So you do. Now what you got here? Tell me. So everybody able to understood it or not? Please do not hesitate to ask me. That is the thing. If you are keeping in your mind that you are still not understanding, that is a very bad thing actually. Still not able to understood what is going on, what is these values, what are.
Sir.
Yes.
So I'm getting different value for D.
Okay, so please check it whether this is correct or not, because this is simple K inversion. Okay. So that depends upon how you constructed the K matrix. What is your degrees of freedom? You have constructed this one x1, x2, x3 or what? And the sequence may be different, right? I have written M1, M2, M3. Be careful about that, okay? The last class you have done, right? Mass and stiffness matrix you have constructed, and that is very one of the simplest 3 degrees of freedom system. Okay. So please construct the mass and stiffness matrix, then find out the K inversion. Okay. Then tell me what. This D matrix is correct or not? Anybody else?
But I also got different values.
Huh?
I also got different value, B matrix.
You are getting different values.
Yes, sir.
So the guy who has told me this one, so please check it. Okay.
Okay, sir.
So what D value you are getting? Let me.
So 1, 2, 2.
1 minute. First of all, tell me these parameters are correctly written by me or not? K1, K2, K3, 1, M1, 1, M2, 2, and M3, 2. This is the what we have done in the last class.
Yes, sir.
Sure.
Yes, yes.
So this is the model, right? M1, M2, M3, K1, K2, K3. This is X1, X2, X3 is the displacement. Now tell me what is your mass matrix?
The diagonal matrix 1, 2, 2.
Okay. What is your K?
2 minus 1 0.
2.
Yes, sir.
So no, sir, it will be 1 minus 1 0, sir.
Who is saying it? How it is 2? It is coming. Where is 2? What is your degrees of freedom? You tell me. How you are choosing the degrees of freedom? X1, X2, X3 or X1, X2? Which way you are assigning? That depends, right?
Sir, by the given condition, like as if like you are writing that yeah, M1 will be like in the top, so it will be like 1 minus 1 0, minus 1 2 minus 1 0 minus
0 minus 1 2, right?
yes, sir, 2, sir. And then I think the D matrix will be same as what I said.
Yes. Please don't. I mean, what is code should I say? Please do not copy or copy means don't just remember that this is my form of mass matrix M1, M2, M3. Then that's why in assignment also I can see some people are writing without calculation. Generalized mass matrix, this is generalized stiffness matrix minus K2, K2, K3 or something like that. Why? I mean, it is not like that. It depends upon the the degrees of freedom sequence. Okay. I think the way you are saying uh, is like this. Not practicing, that is the problem. So they are thinking this is M1, this is M2, this is M3, this is K1, this is K2, this is K3. Then they are adding X1, X2, X3. So then your accordingly, you see, you can say your K matrix is 2 something, that is correct, no problem. But then your mass matrix should be different, right? Mass matrix should be 2, 2, 1. Am I right or wrong?
Right, sir.
Yes. So be careful about that and go by logical. You have understood, I know. You have understood the thing. So just proper manner. Either while using a free body diagram, just use the free body diagram properly and write the equation of motion or Lagrange approach, whatever it is, but in a consistent manner, in a logical manner. Okay. Not by remembering some formulas that will be K1 plus K2 minus K2 minus K2. Not like that. Okay. Okay. So if my dynamic matrix is correct now, please tell me what is this entry. So this is the D into U is this, 17 common, this is this, now I will multiply D into U2, where my U2 is this. Now tell me what is the entry, quick. Use your calculator and tell me what is this multiplication. If you spend a regular basis a little bit of time, let's say half an hour on this subject, okay, on a regular basis, or at least the days the class is there, and if you finish those part only, it will be a very simple subject for you. I mean, at the elementary level at least, not at the higher level, but at the elementary level.
So 8.0584,
8 point
0584, 7.0584,
7.05, 8.0 something. Then last one,
8.0584, 8.0584,
last one,
4.176.
176. So then you common these to make it 1, 8.05, 1. Then other. Repeat this. This multiplied by again you d. Take it and do it. So now not converging, right? 17 and 18, not at all converging. So just repeat the procedure. See after 5 iterations what is happening. Quickly do it. You have the calculator. And you are smart enough and good enough to do the calculation very fast. Okay. So please do it. Anybody has any difficulty in understanding what is the procedure and why the D matrix is like this? Why what is happening in each step, or how to get the natural frequency? I mean, first the eigenvalue lambda you will get, because then you will get the 1 by omega square. Any difficulty? No difficulty. So please do the calculation quickly, because here it is nothing concept wise, nothing is there. It is just calculation.
So I'm getting 7.5404.
7.54.
Yes, sir, 7.5404, 6.5404, 3.7884.
What you are taking? In the next time you are talking about, right?
Yes, sir, in the next iteration.
Yes, please continue. Okay. So D into U3 you are telling that
7.5404.
7.04 then
6.5404.
6.5404.
Yes, sir. And then 3.7884.
7884.
84. Yes, sir.
Then come on this 7.5404. 1 whatever value you are getting. This will be your U4. Again repeat D into U4. 7.54. What is there in the last? 8.05. You see now it is coming close. So you see how fast it is trying to convert it. So 17, then 8.05, then 7.54. Let us see in the next phase what is happening. D into U4. Everybody understanding or not? These are some calculation. Okay, that's all. Maybe you are not able to do it quickly. That is another issue. But are you able to understand what is going on in the process?
So 7.4774.
7.47. You see now it's come closer.
4744. 7.4744.
Then
6.4744.
6.4744.
3.7396.
7396. Then you take out common 7.4744. 1. You see now where it come closer, right? Okay, you can stop it here, but you should not. You go for one more iteration. So this will be your U5. Then you do into U5 and do repeat the procedure and tell me what you are getting the common. That is the beauty of the method. You see, you start with any arbitrary vector. He has taken 1, 2, 3. You just choose 1, 1, 1. Actually, in fact, I have chosen 1, 1, 1. Okay. I have write a MATLAB code and I just chosen 1, 1, 1. And I have given the criteria that stop the iteration when the difference between this and this, I mean the previous one with the present one becomes 1%, less than 1%, the difference. I have chosen 1, 1, 1. So you can do 1, 2, 3 or whatever you choose. You will get the fundamental frequency.
So 7.4665.
7.46.
4658. 4658.
And 1 and something. So now let us stop it here because that you can calculation you can do. Now tell me what is omega you are getting. If this is your lambda.
Point 366.
Huh?
0.366.
Yes. 0.366, right?
Yes, sir.
You see how beautiful it is. Okay. So lambda you got 7.4658. And then you got omega. And that is what you obtain, right? Using Holzer method. And Dunkerel is giving lower value because that will obviously give 0.33. And you can check what is the exact value by the solving the polynomial. Okay. And this will be whatever at the last you will get this vector after taking common, that will be your first eigenvector. But not mass normalized, that will be just normal the typical eigenvector. Okay, you have to mass normalize it later. So you understood the procedure, how to find out the fundamental frequency and how elegant, the beautiful approach you see. Right? So if you write a code, then it will be just very simple, right? You have to just give one input and just take the first one common out, and then you will get whenever it is common. So you start with 17, right? And within 3 iterations, you see 3 or 4 iterations, you converge it. You see the difference 7.4744, 4658, right? You can go further to refine it. Okay. Is it clear to everybody or not?
Yes, sir.
Yes. Very interesting, right? Now, how to find out the other frequencies and modes? That is also required, right? Second mode or second frequency, how to find it? Because if you again start with that same problem, that is D into, what is the problem? D into U is equals to U, right? That is the problem, right? Standard eigenvalue problem, right? D is constant, that is K inverse, that you already obtained. No matter whatever you are choosing, you are getting the highest value of lambda, that is the lowest value of omega square, right? So you will always lead to this. Now how to find out the other one? Okay. So basically you have to remove the contribution or the first mode. Actually you see, so here the first mode is inserted, right? All modes are there. So you have to remove that contribution from the first mode from this matrix. Remove it so that it will never converge to that mode. Okay. It will converge to the next highest value of lambda or the next lowest value of the omega. Understood? So how to the procedure is called the matrix deflation. That's why this procedure, that is the, I'm calling it as a matrix iteration method, is also sometimes called the matrix deflation method. What is the matrix deflation? So it's called the deflation approach. How to deflate it? So now you have to find out D2. So D2, just remember the formula, okay? D2 equals to D1 minus, D1 is nothing but what? Your first D. D1 is D, okay? The original D matrix, that is K inverse. D2 equal to D1 minus lambda 1, that is the first one that you got, okay? Then U1 transpose and M. Remember carefully that this has to be mass normalized. Basically, the first mode thing you have to remove from that. Okay, you see lambda 1 is related to first mode, right? U1 transpose and M. You just deduct it from the D matrix. D1 is nothing but D, right? Then you get the D2. And then you start the iteration using this matrix. Okay. Then you do again the same thing, but instead of D, you use this. Then choose any vector again you. Repeat the procedure, you will get the second frequency. That's guaranteed. Okay. So in general, so your deflated matrix will be, so if you want to ith case, it will be D I minus 1, lambda I minus 1, Ui minus 1, Ui minus 1 transpose and mass matrix. Okay. So that is the deflation you will do. So as an example, I have shown D2. So that is you want to find out also lambda 2 or basically the omega 2. Okay. Because lambda 2 means 1 by omega 2 square. Okay. So D2 equals to D1. D1 is nothing but your D. That's the initial starting D. Okay. So then your D3 will be D2 minus that. D2 is that you obtain here. Okay. In this way. Clear? So you can do it now. If you can do it quickly, okay, or check whether you are able to achieve the second mode or not, second frequency. Okay. So just take a simple example. So what I will suggest, okay, so I have given you one example right here, a simple example. Okay, you can choose another example, 3x3 system, because you can do only calculator by 3x3 system, right? And try to solve the frequencies and modes if wherever applicable using the Rallies method, Holzer method, then matrix iteration method. Okay, then it will be clear to you and you will feel then you have understood the problem. Okay. Remember carefully here that you need to be mass normalized. Okay. The U that you will get from here will not be in general mass normalized. So you have to mass normalize it to deflate the dynamical matrix to go for the second mode. Okay. But otherwise, if you start with this, no matter what you choose, you will always lead to this. Okay. So you have to deflate the matrix. Okay. So from the D1, that is D, you have to deflate the matrix. Again, for the next time, it will be D3 equals to D2 minus lambda 2 into U2 transpose into M to get the third. And so on and so forth for n degrees of freedom system. Is the method interesting or not? Okay.
Yes, sir.
So that is called matrix iteration method. So, but the problem with this is, or the Holzer method is that, you see, at a time we are getting one, right? One frequency modes. You see, first you have to do this one. What is that? I mean that with D matrix, then you have to deflate it. Then you'll get another set, then the next set, and even for Holzer also, right? One by one you have to do iteration and get the first mode steps, first mode frequency, second mode, and third. Okay. So next will be coming the what is called, that I am not going to discuss today because it will be we will confuse with that. Okay, that is called the Jacobi's method. Just I'll give the idea of what it is. Jacobi's method. Okay. It is invented by Carl Gustav Jacob Jacobi. Okay. So it is called the Jacobi's method, and if you do the procedure, follow the procedure, you will get one final matrix. From there you will get the all the eigenvalues and all the eigenvectors. Okay. But you have to do not by single step approach, many steps, but finally you will get everything at a time. Okay. But there are some issues still there, but we'll discuss this method, Jacobi's method, how to find out that. Okay. But the condition is that your D matrix, right? The D into what? U is equals to lambda into U, right? That is the standard eigenvalue problem. How you got this? From the general eigenvalue problem. D is equals to my K inverse M, right? Okay. So the D matrix has to be symmetric. Okay. But in general, although K and M are symmetric, K inverse M is not a symmetric matrix. Okay. So D is not symmetric. But to apply the Jacobi method, it has to be D has to be symmetric matrix. So there are different mathematical procedures there to convert this D matrix. I mean, that's actually decomposition. I don't know whether you have learned it or not in the linear algebra. Okay, like Cholesky factorization. Have you heard about this term, Cholesky factorization?
Yes, sir.
Yes. So through this decomposition, Cholesky decomposition, okay, writing the matrix in upper triangular and lower triangular form. So you can, but I will not go into that. Okay. So you can actually decompose it, and then finally you can convert this D matrix to the symmetric matrix. And once you got a symmetric D matrix, then you can use this for the Jacobi method. Okay. Because remember carefully, the D matrix has to be real symmetric to apply the Jacobi's method. Okay. So this was actually very good method, but the thing is that historically, although it is invented in the year of around 1850s, if I am not wrong, it will be around 1846 or 48. Okay, around something like that, 46 or 48. But this method becomes popular in the year of when? Around 1950s. After 100 years, it's become popular because it requires some computer or something, okay? Because otherwise it will be difficult to hand calculation. So so obviously in class we will not be able to solve it. So this I'll just give you the idea of what is that method itself, okay, and how to convert the non-symmetric D matrix to the D matrix is through the Cholesky decomposition, okay, or Cholesky factorization, okay. So once you got the symmetric D matrix, then you can apply the Jacobi's method, and we will discuss what is that Jacobi method in the tomorrow's class, okay. And then the final method that will be remaining, the Rallies method, that you need to understand, okay. Rallies method, I mean theory behind that also understand, and that is such a beautiful idea. Again, we will start with everything will start from there only. That this eigenvalue problem, K into U equal to omega square. You are not able to understand how powerful this and the orthogonality of the modes. Okay, so Rayleigh will start from this, and we will make such a conclusion that we will get shocked at first time. Okay, that we'll discuss in the Rayleigh's method. Okay. So tomorrow we will discuss about the Jacobi's method very quickly. Okay, and if you understood, that requires computer to solve. Okay. But I will give you the basic understanding or theory behind that. Then we will start the Rallies method. And once Rallies method is done, this chapter, like the determination of the natural frequencies and mode sets, will be over. Okay. And we will move to the next to the final topic on continuous system or distributed parameter system. And as per your syllabus, it is only the beam, and that is also Euler-Bernoulli beam. Okay. So that will make our life easier. Okay. So we will again talk about how to formulate the equation of motion. Okay, and in that case only we learn using the Newtonian's approach or free body diagram. Okay, we will not go to the Hamilton principle. That will be complicated for you. Okay, so we'll just start with the beam problem, and that is Euler-Bernoulli beam. That is without shear deformation. What is the assumption in the Euler-Bernoulli beam? Basic assumption. What is the basic assumption in the Euler-Bernoulli beam? Some people are thinking, sir, went to the beam.
The no shear deformations and plane sections remain plane.
Plane section
Remain plane after bending, and no shear deformations remain.
Yeah, that I mean plane section, even plane section before deformation and after deformation we remain plane and normal to the neutral surface, right?
Yes.
If not only plane, it will be normal. Okay, that is the basic assumption on the Euler boundary theory. Okay, so unity here it should be plus minus. Now tell me how to write here plus minus 1. Yes. Tell me how to write plus minus here. Plus minus 1. Okay, so any doubt regarding the today's class? So I have shared you the Excel sheet for the Holden method. Okay? So that you please practice or make convenient another Excel sheet as you like. Okay, and practice one different problem than the one we have discussed in the class with different parameters. Okay, so just do it. First solve it the exact problem. I mean,
Sir,
exact.
shouldn't be U1 transpose U.
Huh?
It will be like UI minus 1 transpose UI minus 1. Yeah.
No, this is like that only. Okay, this is like that only. But don't ask me how it is coming, or if you want to ask about this, why this sentence. It can be shown that the eigenvalue analysis of equation 12 always converges to the highest number. Why it is? So that is a mathematical phenomenon, linear algebra. If you are interested, then you can see, although not required at your level, computational methods in structural dynamics. You see, the computational method itself a book, okay, in structural dynamics, finding of natural frequency, mode shape, those things itself is a book, and some other things also in structural dynamics. Some other authors are there, but you can refer to that again, that Leonhard Meyrovich. Spelling. You can refer it. If you want to know how it is coming, what is the deflection procedure that will not converge to the previous modes, shapes and frequencies, and why it is always converged to the highest value of lambda. So that mathematical theory you want to learn, then you please refer to the computational method in structural dynamics by Leonhard Meyrovich. There are some other books is available there. There you might also find it. Okay, the computational method. Okay, but at this level it is good enough to remember the procedure. Okay. Any doubt? Okay, so the procedure that I have discussed, it is written here, but if you do not attend the classes, it will be difficult for you to understand by reading this. Okay, at the first time. Now you have understood the procedure. Actually, you don't have to read these also. The same thing is written here. So if everything is clear to you, I'll stop it here. Okay, very good. Thank you.
Thank you, sir.